The European Space Agency has released images showing the interstellar object believed to be a comet.
The story begins with a visitor from beyond, speeding into our solar neighborhood with a trajectory that could only come from outside. On the 1st of July 2025, the survey telescope system known as Asteroid Terrestrial Impact Last Alert System ATLAS flagged an object on a hyperbolic path whose speed and angle revealed it was not bound to our sun. Subsequent analysis showed that this was only the third interstellar object ever documented. The sun's gravity would bend it, but not hold it. It was named 3I Atlas, where 3I indicates third known interstellar. From its initial detection, its motion, composition, and origin promised to deliver something extraordinary. Before we start, smash the like and subscribe buttons for more updates. From the moment of discovery, astronomers around the world mobilized telescopes, both ground-based and orbiting, to track every nuance of its approach. The very idea of a body formed in some other star system, drifting into ours, raises profound questions about planetary system formation, interstellar exchange of material, and the nature of icy bodies in the galaxy. As it descended toward its closest point to the sun, its perihelion, scientists braced for a spectacular interplay of heat, radiation, outgassing, and cosmic travel that might yield clues no object from our solar system could offer. On the 29th of October, 2025, approximate date 3I Atlas reached perihelion at a distance of about 1.36 astronomical units from the Sun between the orbits of Earth and Mars. At that moment, its velocity relative to the Sun was enormous, reflecting the combination of its original interstellar speed and solar capture dynamics. For the human observers on Earth, it marked a turning point, a crucial moment when radiation and solar wind would heat the object intensely, trigger sublimation of ices, activate dust and gas jets, and possibly transform its appearance dramatically. The daring aspect of this event is that not only did NASA and its partner observatories schedule tracking of the comet, but telescopes all over Earth and in space united in their gaze. Every instrument capable of detection had turned toward it. Observatories in Chile, Hawaii, Europe, and elsewhere captured its coma and tail formation. The orbiting Hubble Space Telescope and others provided high-resolution images, yielding tight constraints on the nucleus size, mass loss rates, and activity levels. This near-global network of observation gave an unprecedented coordinated data set for an interstellar visitor. What makes this perihelion event so significant lies in the combination of exceptional circumstances. First, 3I Atlas isn't a typical solar system comet. Its hyperbolic orbit, extreme speed, and probable extrasolar origin elevate it to a fundamentally different category. Its composition appears to include significant carbon dioxide, water ice, dust, and possibly other volatiles that have been exposed to cosmic travel between stars. Second, its passage close to the Sun ensures the heating and outgassing will be intense, generating phenomena uncommon for comets that linger far out in the solar system. The perihelion acts as a crucible. Solar energy blasts the surface and interior, liberating material that has perhaps been frozen for billions of years in deep space. Third, the worldwide observational coverage means that when the event plays out, we will have data from all possible angles and instruments. Ground-based telescopes, space telescopes, spectrometers, polarimeters, and even planetary probes may catch its journey. As 3I Atlas approached perihelion, observers reported increasing activity, a developing coma, dust tail formation, jets, and indications of material being shed at rates that hinted at a substantial nucleus. For example, the high-resolution Hubble observations estimated a dust mass loss rate between 6 and 60 kilograms per second, depending on particle size. The nucleus size was limited to less than about 2.8 kilometers in radius under certain albedo assumptions. That scale makes this object substantial, particularly considering its interstellar origin. The implications of the perihelion event are manifold. On the one hand, it offers an intimate look at material that originated far beyond our solar system. When the sun's heat begins to strip away volatile ices and dust, what emerges is a natural time capsule of another stellar system. The chemistry of the outgassed material, the dust composition, the tail morphology, all become direct data about the environment in which the object formed. Observations of carbon dioxide dominance and water ice presence suggest that 3I Atlas may have formed in a region that experienced intense thermal processing, or perhaps was ejected after long residence near its original star, implying an age possibly older than our own solar system. On another level, the dynamics of the object's interaction with solar radiation and wind give insight into comet physics in a regime not normally accessible. objects that did not evolve in our system and thus may differ in structural strength, composition layering, dust-to-gas ratio, or fragmentation behavior. One of the global observatory's tasks at perihelion was to monitor for fragmentation or breakup. Some interstellar bodies may be weakly bound aggregates of ice and dust, vulnerable to heating and spin-up effects from solar radiation. Should 3I Atlas fragment, we would witness the breakup of an interstellar visitor, a phenomenon that could reveal internal structure, strength, and formation history. Observers noted that spacecraft and Earth's telescopes were poised to capture such an event. Because its orbital path aligned close to the ecliptic plane and its perihelion distance was moderate rather than extremely close to the Sun, the event sits at a sweet spot for acquisition of such data. Moreover, the way the tail and coma develop illustrate how solar heating triggers sublimation, dust ejection, and solar wind sculpting of the material. For 3I Atlas, the expectation was that its coma and tail would evolve rapidly as the Sun's proximity increased. As documented by early August, the object already showed signs of a dust envelope and tail. During the actual perihelion passage, the angle and brightness of the tail, the direction of outflow, and the polarization of scattered sunlight off the dust, a measure of grain size, composition, and structure, all become measurable. Indeed, polarimetric observations indicated a deep and narrow negative polarization branch that is unprecedented among solar system comets and asteroids, implying potentially a different grain structure or dust composition. This suggests that the material's history, grain formation, irradiation, and ejection all differ from typical comets we've studied. An allied implication lies in planetary defense and our understanding of small bodies in the solar system. While 3I Atlas poses no threat to Earth, its closest approach is still quite far. The methods of tracking, observing, and characterizing such a body are exactly those we use for potentially hazardous comets. The perihelion event therefore acts as a rehearsal of sorts. The agencies, telescopes, and data pipelines are being tested under real conditions. Comprehensive monitoring of an inbound interstellar object at perihelion helps refine techniques of orbit determination, non-gravitational force measurement, dust-gas flux estimation, and tail morphology modeling. All this advances our capacity to respond to objects whose origins might differ fundamentally from the main belt asteroids and Kuiper-Oort comets. Beyond the purely technical, the event resonates deeply with the question of how interstellar material might mingle with our solar system. If objects like 3I Atlas can enter our system and be observed in detail, then the possibility rises that our solar system is not an isolated fortress, but a dynamic club of exchange, where objects wander in and out. The perihelion pass, when the object becomes most active and hence most visible, is the window into that epoch. It means we are not only observing a visitor, but capturing a process, the irradiation, heating, and transformation of an object that spent eons beyond the Sun's domain. The timing of the perihelion further heightens its significance. Because this object will cross behind the Sun from Earth's point of view around perihelion, it places constraints on what we can see, but also emphasizes how clever scheduling of telescopes, including space-based instruments and those on the far side of Earth, had to be arranged. Some of the most critical observations happen when the object is near the Sun in the sky, where glare, solar conjunction, and elongation issues challenge observation. Nonetheless, the fact that every capable telescope turned to watch means that few phenomena will escape detection. High-cadence imaging, spectroscopy, polarimetry, and dust-gas monitoring will permit a near-complete record of the transformation that perihelion triggers. Reflecting on the nature of the transformation, one major question is how 3I Atlas's surface and interior respond to solar heating after an interstellar journey. Does it behave like a typical solar system comet, shedding material in a predictable arc of activity? Or does it surprise us, perhaps by releasing dust bursts, fracturing, spinning up, or showing jetting from deeper layers? The perihelion event invites us to test these extremes. If the body is a condensed relic from its parent star system with minimal thermal processing, the heating may expose virgin layers, bright outbursts, unusual volatiles, or structural disintegration. If, on the other hand, the body has already been heavily processed or has a robust nucleus, the activity may be more muted and the tail formation conventional. The detailed observations surrounding perihelion enable scientists to categorize which case is closer to reality. At a deeper level, the perihelion event of 3I Atlas also recalibrates our expectations of comet diversity. In our solar system, We have a catalog of comet types, long period, short period, dynamically new, Jupiter family, etc., and the activity patterns, nucleus properties, and compositions broadly cluster within familiar ranges. But an interstellar object is by definition outside that taxonomy. The perihelion passage acts as the test. Will the object fit within our known models or force us to expand them? The polarimetric peculiarity already hints at the latter. The outgassing chemistry reveals possible differences in volatile inventory, for example, high CO2 relative to CO, or unusual dust-gas ratios compared to typical comets that form near the Sun. Each deviation points toward the fact that comets and other planetary systems may evolve under very different conditions: different star age, stellar radiation, planet scattering, galactic environment, and yet provide parallels to ours. Another powerful implication is the once-in-a-lifetime nature of the event. Most comets we study are native to the solar system and may revisit or reside for many orbits. An interstellar object like 3Y Atlas, however, passes through, never to return. The perihelion is the apex of its visibility and scientific yield. After that, it recedes, fades, and the opportunity shrinks. Bringing every major telescope into play means capturing as much of this fleeting moment as possible. The synergy of observations, optical, infrared, radio, space-based, ground-based, around perihelion effectively turns the Sun's heating zone into a laboratory for extrasolar material. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on NASA's new 3I Atlas discovery? What do you expect happened? We want to hear from you. Thank you for watching and see you next time.